Now we'll talk about limited dependent variable models, where our y variable takes a value of just 0 or 1. Now it can be extended to cases where y takes only some limited number of values, maybe 0, 1, 2, 3, but for now we'll stick with the simplest case. Y can take a value of just 0 or 1. Could mean the y variable answers any variety of yes-no questions. One modeling strategy would just use OLS. Ignore the fact it's going to predict values of y which might be greater than 1 or less than 0. And that's actually not a crazy idea. The basic linear model has lots of other strengths. Mark Bellamy gives a good roundup. But there are other options as well. So often the case, it's a trade-off. Another modeling method is called logit or probit, which are two possible ways to bend the function so it asymptotes towards 1 as the x variables get higher, but asymptotes towards 0 as the x variables get lower. It doesn't actually cross to be higher than 1 or less than 0. It looks more like a CDF, a cumulative distribution function. The way we set this up, we say there's some probability of y being equal to 1, conditional on a set of x variables. We'll combine those x variables in the usual linear way that we understand. The function we'll generically label as f can have additional bends. So this setup includes our standard OLS as a special case. If the function is just the identity, we'd have simple ordinary least squares. But here we're going to twist it around and use a somewhat more complicated f function. The logit function looks kind of complicated. It's 1 over 1 plus e to the minus z. The probit is phi of z, where phi, that Greek letter there, is the cumulative distribution function of the standard normal. The graph above shows the PDF, not the CDF, but we should all be used to going between these now, the PDF of the logit and the probit functions. They look very similar. If you squint hard, you can find some differences. The probit is the lighter one in that picture with a little more of the mass in the shoulders, a little bit lower right at the central point. The tails are slightly different, but in most situations, it's not a huge difference. Now there's some computational complexity. The standard normal is a little bit more difficult for the computer to compute, so logit functions are a bit more common. But that's mostly a relic of the old days when computers were slower. Later, we'll talk about different machine learning techniques that are significantly more intensive to compute. In assessing how the different models perform, we have, unfortunately, more options available. We don't have the simple R-squared measure. Various types of pseudo R-squared have been proposed, but they're often not very useful. They push the important questions into the background. Which miss is worse? Is it worse to predict yes when the true value is no, or to predict no when the true value is yes? You remember we used the terminology of false negative or false positive, type 1 versus type 2 errors. Yes, statisticians are really exciting people with fascinating names for these things. In general, we might not have a symmetric loss function that would penalize false positives and false negatives at equally bad. Remember our little happy face versus poopy chart? The rows are whether an observation is predicted equal to 1 or 0. Columns are whether that observation is actually 1 or actually 0. On the main diagonal, we have happy faces, poop in the off diagonal. You have to answer which poop is worse. Which of the bad outcomes is bad or worse? Depending on what you're using this model for, those may be very different. If you're modeling whether it's worthwhile to show an advertisement to somebody online, well, if you've ever been online, you've noticed a lot of ads don't fit you. But from somebody's perspective, that's not a big loss compared with the possible revenue gain from acquiring a new customer. In other cases, I don't know, maybe part of the national security apparatus is trying to figure out whether to go arrest somebody. That's a different loss function. A subsidiary part to all that is figure out what predicted probability will be interpreted as y equals 1. Typically, the cutoff is 50%, but depending on the case and the loss function, you might want a different cutoff. You can experiment. So how do we do this in R? First, I'll note this is the first, not the last, time when you'll see that you're learning about how to call the LM function can transfer over. R uses the same basic syntax of how to specify a regression function in LM and in GLM and many others. The basic Y twiddle X comes up in lots and lots of other situations. Here, instead of LM, we write GLM, one extra letter there. It's a generalized linear model. Then we distinguish logit and probit in the family, where that is either binomial for logit or for a probit, family equals binomial link probit, which is kind of ugly, I admit. Either of these commands will give you a bunch of summary estimates that look incredibly similar to the simple linear regression output. Get coefficients and standard errors and t-stats and p-values, stars and all. Even the interpretation is actually very similar. If you want to do t-tests on particular coefficient estimates, see if they're statistically significantly different from 0, it's the same procedure. The interpretation is a little more complicated because the slope is going to be different for different values of the x variables. The function's not linear. Whether it's logit or probit, it's got that bendy kind of shape that I've sketched up there at top. Depending on the value of x, the change in the predicted value of y can be very different. For some people, this is basically just diminishing returns. If somebody's already got a whole bunch of other x variables that put them at a very high probability of some outcome, then adding a little more doesn't do much. Going from 96% probability to 97% probability, that doesn't move the needle. Whereas a change from 49% to 51%, maybe that's a huge difference. As earlier, where we discussed about how to interpret linear models with interactions, often the best way to understand is to choose some examples and work out the predicted probabilities. You can calculate how does a little change in the x variable change the calculated probability. In that graph, point like x1, probability doesn't change very much. That person has a low probability of outcome regardless. But at x2, on the other hand, that point is where the slope is nearly at its maximum, so you'd see large changes. Now, it can be difficult to interpret all these coefficient estimates, but I've said before, you're now at the point where getting some results from R is pretty easy. The hard work is to understand and explain what it all means. I'll conclude with a bit of background. At the beginning of your journey, it's okay if you just think this is magic. It works even if you don't know why. But it's useful to get a little sense for what's behind the magic. When we did OLS, we were able to derive a convenient formula for finding these coefficient values, minimize the squared error. Remember, ordinary least squares. The error term is y minus beta x. Sum those up, and having a nice formula makes things very easy. But if I didn't know the formula, I could find those same estimates with enough computing power. Computer could just randomly pick values and find the ones that minimize the squared error terms. Just pick some numbers for beta, calculate the error, nudge around the values to see whether the errors get better or worse. Similarly, probit or logit is going to find some values of beta that minimize that new revised error term, y minus the function of beta x, where that function f is either the logit function or the probit function. There are lots of other estimators possible that just use a different function there for f. But whatever the function, have the computer find a beta value that minimizes that error. There's a good bit of work done in the background, people in computer science or mathematics, to figure out what is the most efficient way of doing this search. In the old days, when computing power was really limited, efficient algorithms were extremely important. Even in modern cases, though, as computing power goes up, so too does the amount of data that we're working with. Now, the problem's mostly solved for situations you're going to be dealing with, but what's going on in the background is called maximum likelihood estimation. Let me give a real simple example. If I see observations from a normal distribution, then the likelihood of seeing a particular value is just the PDF. I can write that down for two observations where, for now, keep the math easier by assuming sigma equals 1. That's 1 over the square root of 2 pi times e to the minus 1/2 x squared minus mu squared. We deal with the exponent by taking the log. The log function is monotonic, so any value that maximizes the log of a function will also maximize the underlying function itself. Taking the log gives a bunch of constant terms that'll drop out, minus 1/2 x minus mu squared. Then, as you remember from calculus, whenever you want to find a maximum value, you take the derivative and set it equal to 0. Derivative with respect to mu is set equal to 0. With some algebra, we find the best estimate of mu is x1 plus x2 over 2, which is, hey, that's exactly the average. Actually, if we go back in history, the normal distribution, sometimes called the Gaussian distribution, because a mathematician named Gauss figured out this very property. With a little more math, you can do the case for n observations, and then, figure a formula to estimate the standard deviation. Maximizing the likelihood of some probit or logit function is a bit more complicated, but again, people have derived the first and second derivative, so finding the maximum value is quicker. But that's why when you look at the output, it will sometimes give you something about how many steps it took to find the estimate. Occasionally, it might take a long time or not converge. There are various ways to try to solve that problem, maybe twiddling the convergence criteria or just giving it more time. Its default is only make a small number of attempts and then give up. Sometimes you need to have it run longer. We'll do more of that down the road.